And first, I'm going to talk about background. Bridges are normally designed to have a lifespan of 120 years, but engineers have discovered that many bridges do not live up to this lifespan. For example, the ASCE discovered that over 9% of the bridges in the US, which carried 188 million trips per day, are structurally deficient in 2016. Researchers find that these three reasons actually are accountable for this phenomenon: discrepancies between the design and constructed structures, and unexpected rate of material deterioration, and increased traffic volume. To cope with this problem, we need an assessment of the bridge. Traditional assessment relies on visual inspections, which are found with these problems inaccurate due to the subjectivity of the inspectors, and some of the bridge components are not accessible after the construction. And these visual inspections are also irregular and can be very expensive. So we need a more automated and continuous way. As a result, structural health monitoring systems are installed on many bridges nowadays. SHM can be described as a combination of multiple systems, including sensory, modeling, data manipulating, and damage detection. However, this system will generate a huge volume of data. These data are normally ignored by the data owners, and they are left untouched unless there is an issue about the bridge. So my project will focus on the SHM system on the 4th bridges. The 4th bridge, as you can see in the middle, is actually built in the 1960s and closed for major maintenance in December 2015, I think. And the SHM system was installed during that maintenance. Currently, we have data from December 2015 for 36 months. This system has nearly 200 sensors and can produce 24 gigabyte data per month. Methodology. The first methodology is principal component analysis. I think many presenters yesterday has mentioned this. And it has the ability to reduce the dimensionality of the dataset with a few principal components. It's important to us because we have a very high dimensional dataset. Second one is called ARIMA. ARIMA is the model to estimate to predict the trends of the data based on its own history. It's a composite of several statistical models, including autoregressive, moving average, and integrated value. So there are 3 parameters that need to be determined before training any ARIMA model. These parameters will be based on the features of specific dataset. So this is the complete ARIMA model here. Next, I'm moving on to machine learning, and I think many of the presenters have mentioned artificial neural networks. I'm not going to details here. Basically, it can have 3 layers: input, hidden layers, and output layers. The next machine learning method I use is called random forest. A random forest model consists of multiple decision trees. Decision tree is a supervised machine learning method to take in the features of the data and make predictions based on observations. In our case, we will use regression trees, which will give us predict the numerical values. Another type of neural network I want to mention is the recurrent neural network. It's different from the traditional artificial neural network because the output of the hidden layer will feed back to itself, so that the information in the hidden layers will persist. It was designed to recognize patterns in sequence data, for example, text or spoken words. In our case, it's actually the time series data from SHM system. One of the recurrent neural network is very popular, called the long short-term memory, LSTM. The LSTM network is especially capable of learning trend from long sequence. Results. First, we applied the PCA to our raw data. It's actually data from February 2017. It has 127 dimensions. From the results, we can see that 90% of the data can be represented by only three principal components, which means that our data is actually very highly correlated with each other. Next, we applied a ARIMA model on traffic data. On the left is the traffic volume every 30 minutes monitored for 6 months. And to better understanding this data, we decomposed it with from these three perspectives. First is trend, is moving average, is the moving average of traffic volume for a week. And the seasonality shows the traffic data is in a high periodic trend, as we can anticipate that. The residues shows the noise in the data. We can see the most of the residues is at the end of this period. This is actually the Christmas holiday there is a significant drop on traffic volume. So we need to, as I mentioned, we need to find the three parameters. We plot the autocorrelation function ACF and partial autocorrelation function PACF for the data to find moving average parameters and autoregressive parameters. So here, when the line drops to 0 at first time, it's actually the value we want. It's 4 for moving average parameters and 2 for autoregressive parameters. So we use ARIMA 2, 1, and 4 for the training. This is the result of the training. We use 11 weeks of data, which is around 2,600 samples. Here is a zoom in data. If you can see, the blue line is the original data, and the orange line is the predicted value from ARIMA model. So actually, we can see that the prediction is very accurate. And we use, you might probably notice that there is a gap in the data. So we use this method to fill the gaps here. We can see that we managed to achieve the integrity of the dataset by using this model. Okay, next we move on to, okay, there's actually a slide missing. We move on to machine learning method. Here is the string data. The other plot will show that there are actually many gaps in the string. The string data might be caused by the loss of power of the sensors, or there's simply a malfunction. These gaps are very harmful for us when training any machine learning model. So the first steps, we need to deal with these gaps. We actually use machine learning method to fill the gaps. And to make this happen, we need to use correlations between the different sensors to make estimations. Here we choose the correlation data and the prediction set. This is our target to fill these gaps. And you can treat this predicting set as X and the correlated data X as X, and this is Y. Among the correlated data, we have traffic and temperature. This will serve as a representative of the operational and environmental condition of the bridge. Next, we applied two machine learning methods, the random forest and a simple shallow artificial neural network. From the results, we can see that random forest actually have better performance, and it reached the accuracy of 90%. And the simple shallow artificial neural network is only 60%. And we managed to fill the gaps with these two methods. And after using this simple AN, we move on to a more complicated one, the LSTM I just mentioned. This is still traffic data, but in a much more higher sampling rate. It's traffic per 30 seconds. So the trends and period is more complicated. So we move on to LSTM. Instead of throwing all the data to the neural network, we use a technique called sliding window. First, we choose one day of data as X and the next day as Y, and to find the correlations between these 2 days and slide across the data set. We split the data set to 80% for training and 20% for test. So for the neural network, the 20% has never been used. Then after the training finished, we use the 20% for validation. And as you can see here, the predicted trend is actually very fit to the actual trends. This is 2 days of traffic data because we can see the morning rush hour and evening rush hour here. And the model accuracy is actually 94%. This is a typo here. A bit of conclusion. What we have achieved now is to use try different statistic models and machine learning techniques on the data from the fourth road bridge. And the ARIMA model can predict time series data with high seasonality and strong periodic trends. And random forest is actually have better performance than simple ANs. But we believe that if we use deep neural network like and the LSTM, we would have better performance on structured responsive data. The next step, we will also apply our models on the data collected from the Queen's Ferry crossing, which have over 2,000 sensors, including the accelerometers, which does not in the fourth road bridge SHM system. And we will hopefully the data quality of Queen's Ferry is better than fourth road bridge, so that we don't need to deal with so many gaps in the data. At last, I would mention the collaborations we made across from industry and academic. The Transport Scotland is the actual bridge owner, and Amy Consulting and Arup is the bridge managers. We get our data from Jim Fisher's testing. They are doing some similar works using the data. Also, I want to express my gratitude to Professor Carlton Hall from University of Massachusetts Amherst, who has been in support of this project from the very beginning. And we have a new collaborator this year is MIT, the Laboratory of Smart Infrastructure and Sustainability. That's me. Thank you.